Hey. We can do jump over.
Hello, again.
That's the first impression. Yeah. Yeah. They're not here.
Okay, good morning everyone. So here we are for a guest colloquium, and it's a great pleasure for me to introduce to you Dr. Arnab Kundu, who is a prominent astronomer, mostly working in the field of optical astronomy to across all the wavelengths. So Dr. Kundu did his BSc from University of Delhi, did his post-graduation and PhD from University of Maryland, was associated and is still continuing with Michigan State University. And he has a wide range of interests. Actually, when we were interacting, we could find that he has worked into solar system, to stars, to galaxies, to comets. And the most beautiful and aspiring part is that he has been into observation in most of the time. So astronomy is best, it's pleasurable job when you actually observe things out. He has also worked on kind of data analysis, has been associated with, working directly with Hubble Space Telescope. So there is this really, his range is quite big. And he's also interested in music and, many other aspects of human life. So it's really, we are happy to have him over here. Today he will be speaking on something like extrasolar planets and of course with preserving our extraordinary planet. So now we know that it all began in something like I guess 1965 when some radio signals were observed and people thought that okay there must be some signals from alien, uh, some intelligent life, some life should be there. So it is really evolving and a very large, a very hot topic at that point of time. But the precision of these radio signals was so high, up to 10 or 12 places after decimal, that any intelligent life would not have actually achieved that precision. So still the search for planetary systems is going on. Of course, he said that he won't be talking about intelligent life. But let me tell you that there are billions of galaxies in this universe, and every galaxy has got billions of stars in it, billions of suns in them, and every star can potentially have a habitat like Earth. But unfortunately or fortunately, we have not been able to find out any intelligent life till now, but still the search is on because the universe is growing bigger and bigger. We can probe deeper and deeper into the space. And one of the most interesting aspect about extrasolar planets is that it's not only the astronomers, professional ones do, but amateur astronomy also contributes a lot in this particular field. So you don't necessarily have to have a lot of things associated with this domain. If you are interested, if you have hobbies, you can still pursue that. So I think that this is really very interesting in the sense that he is also going to talk about our extraordinary planet, what we are actually doing over here. and how the search of extraplanetary system is becoming important even more. So I invite Dr. Kundu over here, and let's give him a big hand of applause. And let's.
Yeah, before you begin, thank you, Dr. for that introduction and hosting him. Just a disclaimer, I am also a Kundu, but we are not related. Except that we are on the same planet. We are related personalities. Thank you. And good luck. Thanks for visiting us. We might dissolve.
Thanks. Thank you for that lovely introduction to astronomy and everything else, Professor Jha. So my name is Arunav. How I pronounce it depends on which part of the world I'm in, so it's pronounced differently everywhere, but I'll just stick with Arunav right now. So like you said, I'm an astronomer. I worked on everything. So from comets to actually planets, I've worked a little bit of Jupiter and black holes. And what you really do is you look at data, there's lots of data, and you try to get the physics of it. What is happening with a black hole? What is happening with the dynamics of stars? How are you getting the systems you are? How did these things form and evolve? So astronomy is basically applied physics for the most part. So you do lots of physics, and it's different physics depending on which topic you're working on. I worked on galaxy formation, and there it's much more, you're using different data at different wavelengths, but dynamics comes into play when you're looking at that thing. So I'm not going to talk about specific things. I could go into a deep astronomy talk and all of that, but somewhere in the middle of this general topic that I've chosen, there'll be bits and pieces of astronomy that I'll go in there. I'm not going to show any equations. I don't want to bamboozle people with equations, but I'll show you a lot. I'll talk about a lot about the underlying physics, even on the extrasolar planets. And every now and then, we will go off on tangents on other things. I hope not for too long, because then the talk will go too long. So the first part of my talk, I'll talk about extrasolar planets, which is planets outside the solar system, how we discover and what we find. And then I'm going to segue into how unique our own planet is and why we need to preserve it. And as I was putting it together that second part last night, it's my own personal scientific interest, and I find a lot of the tools that we use in astronomy and other stuff in an engineering school like this can be used to help all of that. And we must do it because nobody else is going to do it. And as I was putting it together, I realized I probably bit off more than I could chew because that can be a very, very long talk. But I will show you stuff, and feel free to ask me questions about that. And to some extent, that is almost scientific evangelizing, because I'm going to say this is why. There's a lot of confusion around this climate change, what is important, what is not, what we should do, what we shouldn't do. And I try to distill some of the important things in there. Okay, with that introduction, let's get started with the hunt for extrasolar planets and preserving our extraordinary planet. So whenever you look at the sky, you're looking, there's an element of imagination, there's an element of poetry as to why you are doing it. You want to find the physics, but the questions you get, lots of poets have looked at it, others have. So there's science, but it's motivated by human emotions. So I thought a good place to start is with, not like this. Okay, so a good place to start. Oops, a good place to start is not that. is to start with a poem, and which is Emerson, and he goes, "Teach me your mood, O patient stars, who climb each night the ancient sky, leaving on space no shade, no scars, no trace of age, no fear to die." So that's his description of a star. So let's talk about the stars now and the planets. This planetary system has been known since Copernicus's time. And the planetary system starts with the sun, and then it goes off, and it has all these other planets we all know: Mercury, Venus, Earth, Mars, Jupiter. There have been a few changes along the way. And Pluto is no longer a planet. I can tell you why, but it's simply because nature does not like these very discrete boxes that you have, and there's always in between things, and Pluto happens to be there. So right now, there are 8 planets and a growing number of minor planets. So how are planets formed? You basically, most planets and their host stars basically start with a gas cloud. You have a molecular cloud at some point of time, and it has got all kinds of, it has got mostly hydrogen, it's got helium, it's got heavy molecules and things like that. And this gas cloud is sitting out there. And there are usually generations of gas clouds because what happens is you have stars that form and die, and some of the whatever goes off from the dead star again becomes a gas cloud, which is sometimes enriched in more materials. So this process goes on many times, and new generations of stars are formed and die and go on. But for any specific star, when a star forms, you start with a gas cloud. And then from a gas cloud, what happens is it does have some angular momentum, even if it's moving very slowly. And due to gravitational collapse, the gas cloud tries to, when the gas cloud is large enough, it tries to collapse. As it collapses, that angular momentum has to be conserved. It can't just go away. And typically when it collapses into a disk, because the angular momentum is still there, it's flattening down. In the middle, you find a star, and if there is enough mass, then it actually can trigger nuclear reactions in the center. And so that's where a star forms. And the rest of them, let's see if I can get this to work. So I think this should work. I'm not sure which one will start it. Yeah. So this is just a small video. What happens is, as the gas cloud collapses, you end up with this disk. In the disk, there are due to stochastic variations, there's small areas in which you have a few more objects. And so then the gravity of those few more objects attracts a few more objects. And then you end up basically attracting more things in the ring. And it empties out everything else. If you can start with a maxima, that maxima attracts more and more things. And those more and more things end up being, these various bands end up being planets. Some of them end up being asteroids. It depends on how much your local maxima is. Now, this is a very clean video. This is not how it happens in real life. There's lots of collisions. There are some things at different angles. There are 3-body or n-body interactions, which changes the orbits of various things. But in a very general sense, as the cloud collapses, you end up with a disk. Inside the disk, you have local maxima. Those local maxima is essentially gravitationally attract more things. And you end up with possibly multiple planets. That's how we think planets form. And while it happens, the star is not very stable. Many young stars, they give out bursts of X-rays and other things. They're very variable in optical. It's a very messy system, not like it's shown there. So the question is, we can look at lots of stars. Are there planets around the billions of other stars that Professor Jha just mentioned? And this has always exercised human beings. They've looked up, are there? We know there are stars. The question is, are there? So many early scientists and thinkers and poets, they all basically said, yeah, sure, if you have so many billions of them, surely some of them have planets. And they made attempts to measure it even in the 1800s. In fact, the first reported measurement was from Madras Observatory in the mid-1800s. And they looked at something, and I'll talk about it. They looked at a certain signal, and they said, we think there's a planet around this star. It was basically a spurious observation. You did not have the sensitivity to be able to find it. But there have been lots of false starts over a couple of hundreds of years where people have claimed that there's been planets and there is not. It's a very, very difficult observation. We'll come to why. So why is it difficult to detect planets around other stars? Firstly, the reflected optical lights. Planets don't have their own light. The star has their own light. Planets are lit up by the reflected light of the star. And so this reflected optical light of planets is millions of times fainter than that of the star. So if you look in there, it'll basically wash it out because you have to look at a really bright object and right next to it is a really small object. If you stare at a bulb there, in front of that, you put in a very, very small light, you won't see it. Just think of it in terms of millions. If you have a floodlight and you put a small torch in front of that, you will not see the torch. Think of it in millions of terms and you won't see it. The other problem is even the nearest stars are very far away, and this distance is really, really small. You need extraordinary optical resolution to see something like our solar planet, and there just isn't the technology to resolve it at that thing, even with the latest telescopes that have gone up, and the JWST and all. At least the Earth-sized thing is not that easy. In fact, years ago, I worked on something that's an interferometric mission for NASA, and we did all the preliminary science and preparation, and then it got canceled, which is what happens with funding. But if you did interferometry, you might be able to see it. But the reality is you need indirect methods I'm trying to see how much time I'm taking. Okay, so how do you define an extrasolar planet? It's a very rough definition, and the definition is any object with a mass less than 13 times the mass of Jupiter that revolves around a star. That too is not the complete definition. If you look at the IAU definition, there's a multiple things. But in general, the reason for this 13 is if you have more than that, there is enough mass that you end up having nuclear reactions with deuterium in the center. So basically, the definition is that you don't have any nuclear reactions in the center of the object. It doesn't have its own heat source. It is only losing heat, so that's what it is. And I have written only the first line of the definition, but now there are actually some discoveries of planets that are free-floating. They're not actually around a star. So if you ask questions, I'll talk about it, but I don't want to go too far in that, okay? So so there's a physics department, so you should all be able to, you all know what the Doppler effect is. If you have two stars that are in a binary system, those two stars are moving around each other, around their center of mass. As they're moving around their center of mass, one star is, this one worked. One star is moving away from you, one star is moving towards you, one star is moving away from you. Remember, these are so close that you can't resolve them with the image. So the only thing I can see is a spectrum. The spectrum that I can see is the combined spectrum of both of them, okay? And so if something is moving away from you, if you can find some spectral lines, you will see these spectral lines shift to the red. As it comes back towards you, it will shift to the blue. This object will do the other thing. It will shift to the red. It will shift to the blue. And essentially what you have is, if you have a spectrum and you try to break it up with a spectrograph or a prism or something else, and if you have two stars here, your spectrum will do this. You will see spectral lines that move back and forth. So if I see a spectrum and I follow over time, you can do a lot of physics from this. You can get the mass, you can get the inclination, you can get lots of this. But this is how people look at binary stars. These are almost equal mass stars, which you can't resolve. So this is the same data plot on a graph. And on this y-axis, I'm just showing the radial velocity of the star. I'm just plotting it up over time. And by using these two lines, so one star is going in a sinusoid, it's going away, it's coming down, it's going away, it's coming down, so this. The other star is going in the opposite direction because it's a binary system, so if one is coming towards you. This is basically real data from a binary system. See how much the velocity is, 100 kilometers per second for this binary system.
One point. If we have in addition the cosmic expansion, is the Doppler effect direction?
Yes, but this is very nearby objects. This you are looking in our local universe. So you are looking in our galaxy really close by. If you are looking far away, if you're looking at these recession and all, I mean, there's lots of other systematic effects in there. I'm just showing you a clean signal. Yeah, but there's 50 other things, but not the cosmological thing. That is not an issue because you're just looking at the local universe. So no. So if you want to find planets, you need to find much smaller signals, and let me show you why. Let me actually, yes. So you can use Doppler spectroscopy to find planets. In the case of planets, you have a star and you have a planet, and they move around their common center of mass. This is highly exaggerated. The common center of mass is almost certainly in the center of the planet. In our solar system, if you look at the sun and all the planets, even though Jupiter has a mass, the center of mass changes depending on the orbit of the planet. It's mostly the center of mass is inside the surface of the sun. But it can go up to twice the solar radius. But it's a very small, it's a very small deviation from the solar radius. So if you look at this, you will not see any signal from the planet. You will see only one signal from the star. And what you have to see is whether the signal from the star is changing. Again, I am simplifying this a lot because stars vary on their own. The sun itself varies, and it varies in various modes. And if you actually take a two-dimensional, if you take a two-dimensional image with a Fabry-Perot or something, there are many, many different modes in there. So just because I see this motion doesn't tell you. This is why it's a difficult observation. It's a very small observation, but there are about 500 other ways that all stars vary. You have to eliminate all of those before you say this really small signal is because of a planet. This is why it's been really difficult to find this. So again, I'm showing this signal, and remember, it's 100 kilometers per second. But here is the tricky thing. If you want to say Jupiter, Jupiter changes the sun's velocity by 12 meters per second over 12 years. This is 100 kilometers per second. So you have to get that much smaller. Earth changes the sun's velocity by 0.1 meters per second over a year. So you are talking about orders of magnitude more sensitive observations than what you're doing. So that has always been the problem why you can't find it. So everybody expected the first ever extrasolar planet that you will get will be using this method. Nature does not always agree with us. So the first one that was found was a completely different method. So this is where I'll go all into other bits of astronomy, some of the stuff that I work with sometimes. So this is the Vela pulsar. What is a pulsar? The pulsar is a remnant of a star at the end of its main life. It's an old star. A star has gone through most of its hydrogen burning phase. It has gone through a supernova explosion. After the supernova explosion, you are left with a neutron star. It typically has high magnetic field. The magnetic field is not always aligned with the spin axis. So there's lots of bright stuff that goes around on both sides. And as it spins, this is like a lighthouse. So where each time it comes towards you, you basically see a flash. And this is the Vela pulsar in gamma rays. The thing is, it has gone through all of these, massive explosions. How the heck did it end up with the planet? You would think they would be destroyed. They would dynamically, they will go off. So then people went through and made it and looked at it. We'll talk about it in the next slide. But before we do that, it's a good idea to look at the spectrum, the electromagnetic spectrum, and remind ourselves what we are talking about. I was talking about optical data, and suddenly I'm talking about gamma rays. What are gamma rays? If you look at electromagnetic waves at all signals, electromagnetic waves at all wavelengths, the largest wavelengths electromagnetic signals are radio. A little bit less is infrared. A little bit less shorter wavelength is visible. Shorter is UV. Shorter is X-rays. Shorter is gamma rays. In astronomy, when you're looking at it, you look at these different wavelengths and you're probing different physics. And you see different things, and we will come to these different wavelengths, which is why I wanted to remind you. So the stellar physics changes and all of that. So this object is a gamma ray. It is actually a gamma ray neutron star, basically. So, and what they found is they have a neutron star and they have these ABC. What they looked at is, because the neutron star pulses, you can look at these extraordinary accurate pulsar timing, which is what Professor Jha was talking about. And from that timing, you can say this is not something that a standalone pulsar should do. And you go through there and you really work through the data. And in the data, you see signals of these other pulses, which you say is probably because of planets. So these are the first ones that were found in the early 90s. And the planets were probably formed after the supernova explosion. All the remnants that were left there probably formed the planets after the supernova explosion. The first planet that we saw using this Doppler spectroscopy is 51 Pegasus b, and it is around a normal star. It's a sun-like yellow star. It's about 50 light years away, and the planet was discovered by Doppler method by the Swiss astronomers Mayer and Cuelos. I probably mispronounced it. They were awarded the Nobel Prize actually for this a couple of years back. The interesting thing was, this is going off into history, I was in grad school at that point of time. There's an American group that was also getting a lot of data, but they didn't look at their data because they did not expect the data at the time scale that you got this, and so they missed out on finding it. We'll come back to that. It's because of this. The planet is nothing like anyone expected. The planet is about half the mass of Jupiter, and it's in a 4-day orbit, which means it's really close to the star. Only 0.05 AU, 5% of the distance that Earth is from the star. And it's called a hot Jupiter. Now, the way planet formation, I didn't go into the details, the way planet formation works, you don't expect these gas giants to form that close by. Gas giants are expected to form far away, otherwise the gas would all get blown away with the heat. You expect it to be at Jupiter, Saturn distances. Nobody expected a Jupiter-like object this close to the sun. And so they couldn't have formed there. So the working theory is they've basically moved there because of various instabilities, and you're managing to catch it at the right time, and it will eventually get gobbled up by the sun. So this comes back to the velocities that you actually need to detect. So remember that I showed you the radial velocity earlier. This is hundreds of kilometers. 51 Pegasus B. Trend removed means there's lots of other noise in the data. Data is never that clean. After removing all of that, this is the signal that you get from just looking at the star. It is basically what you found is 50 meters per second. So it is 3 orders of magnitude less than what you would need in a binary star. So this is the first observation you had. It's 50 meters per second you actually saw. After eliminating every other stellar effect, you were left with this. Whatever you think that kind of star does it have its, there are variable stars that have certain kinds of patterns. The star from that family has certain kinds of patterns. After removing everything else, this is the signal you have, which tells you. Yeah, so mass should be less than 130. If it's more than 130, then it's a standalone protostar. Maybe not a star, but a protostar. So since it's less than anything less than this is a planet, but then you also have a lower end cutoff. At some point, it becomes asteroids. So astronomy, when you look at nature, for some reason, most things like to work in square. The power law in square. So things go up, number of objects you have is square. So there is a definition at the other end at what point you don't call it a planet, but it increases. It's a minor planet, there isn't a hard cutoff, let's just say. So the asteroids that we have, minor planet asteroids, so that is more or less the region. We are nowhere close to observing that in the extragalactic thing, so it does not become a problem. Once you start observing that, then that definition will need more thought. So put off problems as long as you can, human nature. So this is the first planet you found using this method. This Gliese 581 is 80 times smaller than 51 Peg. And within 14 years of the first observation, you ended up actually, within 14 years of the observation, you actually could get 80 times smaller. That's how much technology and instruments and everything else improve. And the lowest mass exoplanet, and this is more or less going to your question that we know, is Draugr, which is 2 times the mass of the moon. So we have not got anywhere close to finding that lower end, and then that problem will come up. The smallest known exoplanet, smallest known because the densities can be changed, is Kepler 37b. And some of these are actually planetesimals. So you're starting to get into this problem. They don't call it planet, they actually call it planetesimals. And it's very difficult observations because very small signals. And so these things there's no hard and fast, this is the smallest one, there is a bunch of candidates. And so this is the most convincing candidate. But we are already getting to planetesimals. They're not calling it planets, they're calling it planetesimals because of your question. So
exoplanet, what you're talking about, which are formed from what is called the remnant from supernova explosion.
No, remnant from the initial disk from when the star formed. So supernova explosion just happened to be that one neutron star source, but most of these are, the initial gas cloud is making the sun, and while it's making the sun, there's a disk. You actually, people who do infrared astronomy, they can actually see this disk with infrared things. You see this edge-on disk in the infrared, a lot of this, and you know that's where planets are being formed. So you,
The way we understand the genes criteria, in the GMC, you just form the polars and below certain threshold, it will stop. If you have any that kind of power that
that's pretty much what it is.
from the GMC, it will end up with some kind of planet itself.
No, so the genes mass that you're talking about is that is applicable. So this is not in one molecular cloud. You're forming lots and lots of stars. So it's local genes mass that you're talking about. It's a local genes mass, and each one of them is forming a star. So stars form in clumps inside these molecular gas clouds. If you look at last week's JWST image or the earlier HST image, which has got pillars of creation, those are basically gas clouds, and everywhere on the edges is these stars are forming. So the local genes mass is the genes mass criteria is for the stars, but there's many other forces also acting. It's that genes mass is a simplified version, but there's lots of other radiation pressure and all these other things that are also coming. I'll not get into too much details of that. But the planet part of it is basically just gravitational aggregation in the disk with lots of collisions and gravitation also. Yes, the closest ones around that. So as we are getting better and better instruments, we are going further and further away. But
How far are we now?
Hundreds of light years. I mean, TESS is a observatory that has been sent up in 2018. They are looking at a really big patch of sky. But I just looked it up last night, so they probably will find thousands of them. But they're still working through the data, and they've only confirmed over 122. But the stars are all in a range. So till the data comes out, I don't know what the furthest. But almost certainly from the test data, what you will find is the furthest ones that we will see is from the test data. So this Doppler method is most planets found this method are the hot Jupiters, the ones that are really Jupiters that are really close to the star. But some of it you have to be careful. What you're looking at is a selection effect, because the easiest thing to measure is something really big that's really close by, so it's moving the star by a lot. So just because you saw most of them doesn't mean that's where the universe is. You should not fool yourself by saying this is what the data shows. So you have to do a very careful analysis of the statistical probabilities. And there are these other methods, which I'll talk about now, which are found there. So as of now, about 450 exoplanets have been found using the Doppler method. And as of July 22, there are more than 5,000 exoplanets. If I give this talk next month later, there will be many more. There are 3,700 stellar systems, and 826 of them, as of today, are in multiple systems. So they have found more than one planet in there. It doesn't mean that the others are not multiple. It's just that our signal is enough to find multiple only 826. So what this plot is basically over the years, which you can't see, how many more planets you have discovered. And this basically goes up to a very specialized satellite went up, and it got a bunch of data. The red ones are basically these Doppler methods, and the green and the yellow, I'll talk about these. These are some of the other methods of discovering it. So what you do, and this is when we come back to the Earth, so stars, if you have a 0.1 solar mass star and a 10 solar mass star, if you've taken an astronomy course, if you do the nuclear physics of it, the more massive the star is, the brighter it is. The bluer it is, the hotter it is, the more luminous it is, generally. So these are redder stars, cooler stars. These are hotter, bluer stars as you go up to more and more mass. So basically, whether you can have liquid water depends on how far you are, how much total energy you are getting, insolation. And that will change depending on how bright it is. So whether or not you have liquid water, you have to be further away from the large star to get liquid water. You have to be closer to be in the small. So this zone is where you have, they call it habitable zone, but all that you mean is you can have water in liquid form if you are in this green zone. Now we are thinking, where can you actually have Earth-like terrestrial planets? This is the only one you know, so there is one solar mass and one distance from the Earth. But mostly around here, if you're really close by, if it's really hot, even if you're a planet, its atmosphere boils away. So you end up not having atmospheres. If you're too far away, it's cold. If you're further away, you actually end up getting gas giants. So essentially, there is a very small window where in the habitable zone, you might find Earth-like planets, is what it is, what that plot shows. So, physics department, we should talk about other interesting ways of physics of doing it. There's something called gravitational lensing, and you might be able to find planets doing that, which is, if you have a star at the back, you get the most signal. If you happen to have another star in front, which passes by quickly, as the star passes by, if you study Einstein's gravity, basically space-time ends up being curved. If you have a star at the back, if you have another star that's in halfway in between, the light that was coming from this star was going away in this direction, but this star bends it back towards you. Same thing, light in the other direction, but bends it towards you. So when they are lined up, you end up getting focused light from many directions which would have gone off, which is focused in your direction, so it ends up becoming brighter. You end up getting gravitationally lensed. And if your time scales and distances are right, within 1 or 2 days, as a star moves in front of you, you will see this background star become brighter and become less bright. So you will see a signal like this. If I'm following some stars in the field, and it becomes bright and it becomes less bright. There are certain very specific things to the signal which help you eliminate other variability. If you ask me, I'll go into the details. Let's not go into the gory details right now. So this is gravitational lensing. Here, you will see some brightness. As the lens is in there, it becomes brighter. As it goes there, it becomes less bright. What happens is, if this star also happens to have a planet around it, at some point of time, the planet can also lens that backwards, that star behind and make it a little brighter. So what you will end up having is, you have a signal like this, and then you have another blip in signal in a very short time, which tells you that you have a microlens planet. So few planets have been found. So this is an 8-hour time scale. Over 30 days, there's a star is brightening it. In between, on an 8-hour time scale, the planet brightened it. So some of them, handful of planets have been discovered, but it is not repeatable. You would depend on chance correlation, but it is useful to get statistics. A lot of things in astronomy is, if you get the statistics, I can tell you how many free-floating planets are in there. So it's very useful. Like, there were ideas that dark matter might be things that are getting microlensed that you don't see in the light. So people surveyed large areas of the sky to see, am I seeing lensing? The number of lensing signals you see tells you how many dark objects are floating about. And the answer is, you cannot explain dark matter simply by these unseen black holes or something else floating around. And in that experiment, as a side benefit, you ended up seeing a few planets, also extrasolar planets. But you get statistics. Going off on a tangent, and so gravitational lensing with galaxies. So last week, the JWST put out these images, and I'm sure you saw this one, this one in there. What this is there is a cluster of galaxies here, very, very far away, high redshift. And behind that, there are a lot of these galaxies. These lines that you see, these sort of straight lines, which are more or less in a semicircle around it, these are actually all individual galaxies that are behind the cluster. What the cluster has done is, it has lensed it and distorted it. It is distorted that way because of the lens mass and shape. There are people who analyze it and can tell you by looking at this how much is the mass of the lens. So this is also gravitational lensing, but on a completely different time scale. So if I look at this galaxy, it will actually become brighter and go down what I showed you earlier, but over billions of years, over tens of billions of years, because this cluster of galaxies has to pass in front of all of those galaxies on there. But if I could do this same experiment over billions of years, I would see that same kind of bright signal. So this is going off into other astronomy, but it's interesting in the news, I thought I'd talk about it. So the other thing that you can do is, if you have these stars going past, if you have the right orientation, you can end up eclipsing, the planet can end up eclipsing the star by a little bit. And that is a very useful signal. So in 1999, the first one was basically, the first object was 0.5 Jupiter masses, was actually seen to orbit around, edge on, around the, let me see if I can, I'm not sure if I, this. Yeah. So what this is you have a planet around a star, and this is the light, the total amount of light. So as it goes in there, you're basically seeing the light fall off. And you're seeing an eclipse. That's actually more real data. And you take this over orbits and orbits and orbits, and then you can basically find out various things, the mass of both of the objects by doing this. So, and this is the most promising method to find Earth-sized planets in the habitable zone. It just so happens for many reasons. So I will next. Okay. So what Kepler did, I talked about Kepler a little bit. I have to move on to the next part of it, so I'm looking at the time. So Kepler was designed to find planets around other stars using eclipses. It was a telescope that was designed to do this. And before that, the French Corot satellite was a predecessor. It looked at some of them. Right now, TESS is a specialized satellite that NASA sent up a few years ago, and that data is still being analyzed, and it was specifically sent to do this. And much of this data is public. So what did Kepler do? And this is your question, is if you're looking at sun, this is the whole Milky Way. It looked at a certain arm of star-forming galaxies. It just stared at that same point, and then it looked at this patch of sky, and it looked at all the stars in this patch of sky, and it basically just followed them exquisitely, just photometry. How is the light from each of them changing over years and years? And you get lots of variability. The problem is really finding out which ones are real. That's the hard work, because there's so much other thing. So what Kepler found is, it is so exquisite data that you actually see not just, okay. So as the planet is moving in front, it's doing this, and it's going, so this is basically, the star is lighting up the planet a little bit, and that light is going away, so you see this little dip. Because here it is just eclipsing it. On the other side, you are seeing phases of the planet, essentially. So Kepler is so exquisite that it can actually get not only the dip in front, but the fact that it was lit up here and then that went behind the star, you can actually see that signal. So that's what it did. So Kepler followed 100,000 stars over 105 square degrees to find a few thousand extrasolar planets, actually. So this is what tells you. So the first one that you found, the signal for eclipsing, this is noisy ground-based data, and this is where you think you have an eclipse. This is the first discovery. This is actual Kepler data. This is how much better this space-based data is. This is real Kepler data, which shows you absolutely, without a doubt, that that's what is going on. So then when you magnify, remember how I told you this happens, and this is basically seeing the phase of the planet as it is going around. And you can see that in Kepler data. You see the first dip and you see the second dip. So Kepler has found over 2,500 exoplanets. Some are still being analyzed. So the goal is always to find Earth-like things. So the smallest terrestrial planet found by Corot is called Corot 7b, since it's rocky. Since it's Earth-like, they call it rocky, basically. And this is something about that planet, but it is so close that the surface temperature is 1000 C. So it's kind of like the Earth. It's a terrestrial planet, but it's so close, it's 1000 C. So not exactly an Earth analog. So there have been other planet systems which have, question? No. So there have been other planetary systems which are in the habitable zone, but these are habitable zone on a very different star. You know, all it says is you might have liquid water. So Goldilocks zone. So there have been other things that are close cousins. I won't go into the details. Other things that have been close cousins, but not really Earth-like. You will see lots of these, which are not really Earth-like. So initially I told you that you can't actually find something with direct imaging. Turns out I lied to you. You kind of sort of can if you look at different wavelengths and if you look at things that are far away. So if you look at the Milky Way at different wavelengths, it looks completely different. Stars look completely different from the radio to the gamma rays. And you can use that to your benefit, sort of, to find some planets. If you look at the infrared, what happens is most stars are not as bright in the infrared, but most planets are actually brighter in the infrared. They're relatively bright. It's still a pretty large thing. And if you look far enough, so these are just data in the infrared, I think this is with the Hubble Space Telescope, the star is actually blanked out. At 1.1 micron, around a brown dwarf, you actually see a fairly large planet, but it's very far away. It's nowhere near like our Earth-like system. So there have been some of these. These giant planet candidates are much further than Europe is, much further than Pluto is. So if it's really far away, it's kind of looking at a not very bright star, then you can kind of see images in certain cases. And this is again with the ground-based Keck telescope, and some of them, again, this has been blanked out using various methods. You can see some really far away, large planets. Again, it's a selection bias. You will not find Earth-like planets doing this. They're close to 13 Jupiter and Mars. They're twice the orbital radius of Saturn. So it's really high mass, really far away. If you look at the infrared, you're on the edge of detection, is what it is. So this is also around a normal star. So this is with the HST. They managed to, the star is in there, Fomalhaut is in there. And they actually, the HST, it is so far away, with HST's resolution, you could actually see the movement. So this is in 2004, 2006. But it is at 115 AU. So the only way you can do it is if it's really far away, but not really directly. So I thought the Stegor quote was kind of appropriate. The stars are not afraid to appear like fireflies because that's what you're doing. They're just fireflies at that point, and we're trying to look at this little bit of stars in there. So there's other planets like this that are very far away. Something that is 650 astronomical units. So there's a whole bunch of them. I could keep talking all day, but I'll not do that. But what you've also found is, I showed you that signal. So 55 Cancri, you have this sinusoidal figure. But you look at it and say, why is it noisy? It is very noisy. Essentially, you can go in there and say there's various components. How do you separate them out? And there is lots of degeneracies in there that you have to solve. But when you solve the degeneracies, you can actually divide that out and you can find a bunch of planets using this method. So within that noisy thing, you can find one signal here, one signal here, one signal here. So some are more convincing. People argue about some of the other ones, because whether or not some of the smaller ones are real. So 55 Cancri has 8 times the mass of the Earth and is a terrestrial planet with a molten surface. But you have found 5 different planets with different parameters, how far away, what the eccentricity is, what the semi-major axis is. I would not go through the specific details of those things. So there's a video on this. I don't think we will go through the video. So what you can do, so these are various planets found in there. So the last thing I will talk about with planets is we can study the composition of planets. If you have this kind of eclipse, then what happens is the stats for nerds, that's what I need. So if you have the planet go in front of you, then you basically have some of the gas from the planet covering the surface of the star, and light is coming through that gas cloud. You can do spectroscopy, and you can find out what it is. And what has been seen is, you can do the chemistry of the eclipsing system. It's a very, very difficult observation. This is a spectrum of the star plus planet. When the planet goes in, you have the stellar spectrum. When you divide these two, when you subtract out to these two very large numbers, you get a very small spectrum. You get a very small number, which is the spectrum of the planet. It's always a difficult. You have whatever noise you have the noise in a large signal, subtracting out, getting, and the noise in the small signal is relatively large. So you get this ratty spectrum like this, but the spectrum tells you it's got silicon and oxygen. And for the Spitzer Space Telescope, which is the infrared telescopes, you have seen something that you don't see water signature, but you see SiO. So there will be mostly absorption because you have the planet moving in front of the star. So there's mostly, this is not an emission spectrum. I mean, it's an absorption spectrum, yes. So Spitzer and Hubble, again, they found various lines, and you can say you got methane. Again, JWST actually looked at it 2 days ago, and in the press releases, This is an extrasolar planet, WASP 96b. It's an eclipsing hot Jupiter, and it has been observed in transit. And when you do this, this is the signal you get. It looks like a ratty signal, but even with JWST, this is the best you can get, but you see evidence of water there. There's evidence of water lines in there. I am waiting for the papers to see what it is. There are many different kinds of planets. Some of them show evidence for collisions, and you see the spectral signature of collisions in there. And there are some that have got, like, we have one asteroid belt. There are some that have got two asteroid belts. I will leave that to the question. So I will quickly move to the last bit of my talk otherwise. So yeah, I'll not talk about that. I'll leave that. The solar system holds lessons for life on Earth. So a question for the students. The hottest planet in the solar system is? Yeah, it's not Mercury, it's Venus. And the reason it is Venus is, the surface temperature of Venus is 475 C due to runaway greenhouse effect. And what is the greenhouse effect? The greenhouse effect is short wavelengths of light that are coming in from the sun gets absorbed by the Earth. The longer wavelengths are going up, they're trying to escape, but mostly carbon dioxide. In the case of Venus, 96 or 98% is carbon dioxide. Again, absorbs it and re-radiates it, and it gets trapped. So this is this question for the undergrads. Why is it shorter wavelengths for the sunlight and longer wavelengths on the way out? Any guesses? What is the black body temperature of the sun? 6,000 K. What is the black body temperature of the Earth? It's about 275, 300 K or something. So when you look at black body radiation of a hotter object will be at shorter wavelengths. Black body radiation of a colder object will be at a longer wavelength. So when the Earth re-radiates, the Earth mostly re-radiates in the infrared. So when NASA scientists have looked at it recently, they've said that Venus may have been habitable. This runaway climate change is what heated it up, and now it's a hellhole. All you see is it's really hot, and it has got all of these clouds in there. Mercury's daytime temperature is 430 C, nighttime is 180 C. The reason is Mercury's atmosphere is boiled away. So when it's boiled away, you have a big temperature difference in both sides. So you need an atmosphere to be able to regulate the temperature on a planet. Mars has a very thin atmosphere, average is minus 60 C. No matter what Musk or other billionaires say, Mars is not habitable. You are not terraforming anytime soon. So this is the lesson we should learn from looking at exoplanets and our planet, is you need an atmosphere to regulate the temperature, but in a very narrow range to sustain life. If the Earth did not have its atmosphere, we would be 15 degrees colder. That also would not be good. If you increase a little bit, you will go off into not quite Venus, but in very difficult territory. So the last little bit of my talk, I'll show you this, what we are looking at. Carbon dioxide in the atmosphere since 1960 has been rising very, very fast. This is annual variation, but if you take the annual variation, on average, it is going from 320 parts per billion to 420. And it is a hockey stick, it's going straight up. If you actually look at the atmospheric carbon dioxide and emission, this is how much the emission has increased. And this is the CO2 in parts per million. Till the beginning of the Industrial Revolution in 1750, it was more or less constant. Since then, it's been rising, and it's rising really sharply. And this is because CO2 stays in the atmosphere for hundreds of years. The CO2 from the early Industrial Revolution is still in the atmosphere. If we stopped all the CO2, we would still have the lingering effects of this for hundreds of years. Now, one of the confusing things that people like to say is, well, the Earth has gone through many of this. It has gone through lots of these phases, which is true. The Earth is over hundreds of thousands of years. It has gone back and forth and so forth. But the thing to remember, all of human history, it has been rock steady in the tens of thousands of years. Because of where we are, the temperature has been steady because of the carbon dioxide. Now it is going up at a faster rate than at any other time, and it's almost certainly because of human activity. So the Earth has been unstable, but not on this time scales. Even if you make it unstable, it will eventually come back. So when we talk about we are saving the Earth, we are not saving the Earth. We are saving life on Earth. We are trying to save ourselves. And I think that is a mistake in the way this is always framed when we talk about climate change. Now the thing is, this is not the only thing that happens. There's methane and nitrous oxide. Methane is natural gas, our cooking gas, and the other thing. Methane is much more potent. It's actually 100 times worse as a climate change gas. But it stays for decades. For decades is already bad enough when you're doing this. So you have to look for what happens to methane too. So this is very, very busy. I'm not going to talk about all of this. If you ask me questions, I'll tell you. So what happens is you have heat waves. This is from last night. This is a headline from last night. Heat waves and warning of heat apocalypse in France. We have seen this in India too. There's been heat waves. That's the most obvious signature you see. Another thing that happens is this is a plot of the intensity of cyclones, both in the Bay of Bengal, where it's very, very bad. This particular one is in the Atlantic. And you expect how much energy you have in the cyclones to basically, that some models that say it won't go up very much, but the other models which say it'll go up much more and really fast. The question is, you have the one planet, do you want to take a guess on what will happen? Because there's a very good chance that this is where we are heading. By the time it goes that bad, there's nothing we can do about it. There's the Atlantic meridional overturning circuit. It's a reason circulation is basically various water circulation patterns, which is why Europe is not as cold as it should be, because it keeps it cool. And with climate change, this will end up weakening, and it will change global weather. So climate change is going to make India's monsoons more erratic, and our entire economy depends on the monsoons. And it's going to affect crops within 10 years, that's what the model says. There's permafrost up in the Arctic, and which has always been frozen. That is beginning to melt. Below the permafrost is lots of peat bog and all, where there is lots of methane trapped in. If the permafrost melts, there is some chance all of that methane will go in, and you will have a runaway effect. It's called the Clathrate-Gunn hypothesis. To the best guesses, people think this won't happen, but that's the best guesses based on what's happening now. If it becomes hotter, this might get worse. So by the time it gets there, so I'm just going to wrap up. So I don't want to leave it on a negative tone. So what we can do is we can reduce the carbon footprint of the small fraction of people who emit the overwhelming fraction of greenhouse gases. But you need space for the people at the lower end to grow. And it's actually people like me who are most responsible. Let me give you a number. I flew in from the US. The one flight that I took, one person's seat, if you measure out what the carbon output is, that one back and forth flight is as much as the average emission per year of a person in India. That average person is probably not you, because you guys also have you guys have computers and AC. But imagine how much people at the lower end, how little they use. So it's the rich people making life really difficult for the poor. So we have to get environmentally friendly technology, but we have to be honest about it. Geoengineering, maybe, but because there are risks to it. Policy, in the end, it's policy, and is what matters. For example, I am definitely going over time. I'm going to wrap up in 5 minutes now. Tree planting has mind-blowing. There's studies that are saying if you plant a lot of trees, you can fix it. Except a couple of years ago, the Norwegian government actually, they have green initiatives, and they have actually spent the most on greening, and they looked at some of these things during the Olympics and during everything else. And they found that on average, see, if you plant a tree over maybe 20 or 30 years, that will basically take out the carbon. They followed things over 2 or 3 years, and they found nobody followed it up, and in fact, it actually got worse. And they found, in a practical sense, tree planting did not help, and it might actually make the situation worse. In theory, planting a lot of trees work. In practice, you have to look after those trees for 30 years before any of the payback happens. So you have to be careful about all of that. So there is, in Iceland, they've actually put in this machine which is capturing carbon from the atmosphere. It is using energy to capture this. You can actually buy shares on it. You and I can go spend money and do this carbon capture. The problem is carbon is a very inefficient process. There's parts per million. And it only works in Iceland because they have abundant geothermal energy. This doesn't work everywhere. But it can, and certainly, if you put it next to a power plant, then it might work. So then we talk about electric cars, and I'm not going to go detail in there, but I'll just tell you this, electric cars help, definitely they help, but they only improve the efficiency by about a factor of 2. So it's not like if I have an electric car, I can endlessly drive them. Most of the carbon is front-loaded in the manufacturing, and you have to do life cycle analysis. When you do life cycle analysis, there's a map of the US, you find that they are much less efficient here than in other places, and that's temperature dependent because how efficient the batteries are. And depending on where the power grid is, what this shows is they're not as efficient where I live here in Michigan. They're much more efficient here because the power grid comes from hydroelectric power. So you cannot just build electric cars. You have to do policy, and this is the job of scientists and young people like you to hold everybody's feet to fire and saying, just don't tell me you're getting electric cars, but do all these other things. So I will quickly end. This is the last slide that I have, which is we can use, I have various ideas on this. We use a lot of data, we do imaging, we put up satellites, and there's people who do AI, and a lot of these things you can actually use to help people, and which can be done. Last year there was this glacier burst in Uttarakhand, which is fairly high up in there. How do climatologists do this? They hike up to those mountains, they put sensors on there, and then they see what happens. So this is, ISRO released the image of what happened, but ISRO released this after it happened. There's this private company called Planet that also did this. But there are ways to do it. If you can look at those glaciers in remote places, and if you can get fairly cheap observations from CubeSats and things like that, if you look at it many times, you can probably see the motion of glaciers and things using data, using analysis, and warn people of places that you cannot reach. You cannot go into every high altitude. It's dangerous for people to go in there and put it, but we can actually do it. And I can talk to people later on how you can do it. India has the resources. And in the end, you have to do it yourself. Other countries will not do it. COVID shows us that, right? So when it actually came down to it, rich countries hoarded their own thing. So you have to do it yourself. So I want to end this in a sort of both cautious and hopeful note by Carl Sagan's Pale Blue Dot. This is the most poetic and beautiful thing that there is. I think that's a good place to end, and I will just let it play. Oops, I think.
That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
I couldn't do better than that. So I will just end there and take any, yeah.
Nice presentation. But if you allow me, can I ask reference?
Sure, sure,
Somewhere I'm regarding the chemistry.
sure.
Somewhere I have heard that something happens to the time in the center of the black hole. Is it this little bit of what it is and how it is?
What it is, I mean, the black hole, the way you find black holes is basically you run through these equations of gravity and you end up having a singularity. The equations basically, essentially you don't have any information in there. But when you solve those equations, there is actually one certain solution which shows that you can get the information come out somewhere else. The wormhole there's many different aspects to this question. So I'm wondering which one I should answer in which order. So one of the solutions to these equations basically says you can have a wormhole. You have information in there that comes out somewhere else. So that is one of the solutions. But one of the bigger problems is what happens to information, whether or not it's a naked singularity or not. And there's different schools of thought on what happens to the information at the surface of a black hole. And for example, this is what Stephen Hawking was famous for. So it really goes down to mathematical solutions which may or may not have real world implications. The reality is once a signal goes inside a black hole, we have no way of knowing. The signal cannot escape. We don't know. But there are mathematical solutions that tell you that maybe something else happens. So, but it's not, at that point, it's not in the realm of reality as far as we know, because we have no way of observing it. We have no way of getting the data once something falls in the black hole. But yes, there are various theories on what happens to the information. Go ahead.
Good afternoon, sir. It was a really very good presentation. Basically, I'm a chemist, and whenever I look in the sky and whenever we talk of astronomy, the first thing that attracts me more is a black hole, as what sir said. But I've also heard of white holes. So do they really exist, or it's a myth, or just enlighten us?
The white hole is exactly what not really. There's nothing that you're going to observe. But it is basically this. If the information goes out, sometimes that information can come out somewhere else. So the people who run with this the most are the sci-fi, the ones who make sci-fi movies, because it's a very interesting thing. You can go in and come out somewhere. But as such, no. There is no, I mean, it is a theoretical possibility, but no. Not a very seriously taken one, but the equations do tell you that this could happen. Yeah. Yeah.
From the data to understanding of model, like to getting a model, there are a lot of assumptions, a lot of very minute things. Have you encountered situations in which you interpreted data wrongly? Have you fell into the wrong side?
Yes, this happens all the time in science, but that's the whole point of science. If you make a mistake, then you admit it. That is what people, and you are not, this is why data is public. NASA is making all its data instantly public so that 10 other people can check it and say whether your interpretation was right. What I didn't talk about is before this, in this Doppler method, there was actually a claim before this that they found a planet with the Doppler method, which basically had something like a 6-month period. And they went back, other people look at the data, and what had happened is, you should always be suspicious if it's 6 months, because it's a multiple of the Earth's orbit. And it turned out some little very small correction in the Earth's orbit was not done fully, and what you were seeing is the evidence of some of that. But you make a mistake, and it is not a moral failure. It is a very, very difficult set of things. There's things you miss, there's mistakes you make, but this is why the papers are refereed. This is why second and third people go and look at it to confirm it, is because it's not, I said it, I did this, it must be right. And so things like that happen.
Can I have a couple of questions more?
Carrying forward, talking about review. So, the reviewers actually take a view at data, just trust you to or find errors in the method.
It depends on what it is. Like, so when I have refereed it,
2, 3 years to get a paper published.
yes.
To take long time.
But what you can do is typically, when I look at it saying, there seems to be this couple of things you have not checked. Show me what you get. Show me a simulation of what you are doing. You can do this to a certain extent. You can't. I mean, the problem that comes up is things like LIGO, for example. There's a few thousand people there. Pretty much everybody who knows everything is on the LIGO panel. The people who are reviewing, there's not that many people left to review if everybody's on the panel, and it gets very difficult. So then
becomes a conflict of interest.
it becomes a conflict. So they set up lots of, what LIGO did is, see, when you get a LIGO signal, it is gravitational this, but there's hundreds of things that are, I remember when I was my first postdoc, when they were first looking at LIGO, they showed me signals. And some of this was, trucks going on the highway, sea, tidal thing. You have to eliminate each one of those before you get this tiny signal. So what the LIGO people did is they actually formed teams within themselves. Some of them put in false data without telling anyone else. Only 3 people knew. And then suddenly there was, this rumor, LIGO has found this, that. You want to see if all the other systems are finding what you are putting in the simulations. So LIGO went through 2 or 3 rumors, LIGO has found something, and then those rumors went away on Twitter, because what it was even the people in the LIGO team didn't know it. Somebody had put the false data. Only 3 or 4 people knew that. But that showed the success, that they could find the false data. They put in false data that was not exactly merger of these things. Do you find it? So that gives you some confidence that you have to be very honest that you can make mistakes. And I think that's the difference between science and many other fields is yes, but we have to test it relentlessly. And like Carl Sagan's thing is extraordinary claims need extraordinary evidence, and that's what it is. So there have actually been papers since then in LIGO which is saying this is not actually gravitational lensing, this and that. People have gone back and looked at it. Yes, it is. I think it's perfectly fine to question, even though I think those questions are probably not. I mean, it probably is. Now we've got enough data looking at it. But I think it's a valid question to keep asking.
Different methods.
Yeah. Yeah. Selection bias. I mean, now we know that those kinds of stars are not real. Those kind of planets are not the most. And also because once you find this eclipse thing, that is most promising, because you could eclipse at any distance. So if it's an edge-on system, you could see small planets, large planets, much more. So that is where most of the effort of these new NASA satellites has also gone, because you can find terrestrial planets and everything else. As long as it's edge-on, you will, if you get better and better signals, you will end up seeing various planets. So that's where the effort has also gone. But people are extraordinarily aware of what selection bias is, what fraction of orbits you expect to be edge-on. So then you model that to say, what are the total in there? So I didn't talk about a lot of other physics in there, because some of them are not edge-on. You see certain things going at various angles. And there are what three-body things, Kolmogorov-Lizov resonances, which can actually change orbits and go in opposite directions. I didn't talk about that. Some of them go in opposite directions. How did that happen? You don't expect it to happen. And I can talk about the physics of what happens. There is a one, you conserve only one conserved quantity in one axis, but you can actually exchange angular momentum and inclination. And by doing that, you can flip orbits also. There's lots of physics that goes into all of that. So, but I didn't want to go.
You also tend to believe something which we arrived at.
Yes.
I assume that some of these experiments have been observed by
Absolutely, absolutely. Some of them, like the ones that are spectroscopic, you tend to get the spectroscopic ones and the eclipsing ones. They're more or less the same methods. You will see it in two different ways. Definitely, those are the easiest. Microlensing, you will see it once and gone. But you can look at the advantage of the microlensing signal is when stellar light changes, it usually has the spectrum changes because of whatever it is, because some of these engines, it's like a Carnot cycle or something, gets bluer or redder. If you have gravitational lensing, it is basically gray. All light will go up together and down. So that is a very unusual signal in astronomy. Everything, all wavelengths change together. That tells you it's gravitational lensing. So yeah, I didn't go into those gory details. Go ahead.
Sir, thank you for giving us so much of insights about this knowledge. So my doubt is like how the Indian traditional astronomical knowledge is contributing or correlating to the modern astronomy.
So when I used to be at TIFR, one of my colleagues was into the history of astronomy, and I had very interesting conversations with him. So ancient astronomy, they looked at certain things, they were good at certain things. So the Indian calendar was kind of good. Much of our modern astronomy, the naming conventions and things like that, a lot of it came from Mesopotamia. And India and Mesopotamia had a lot of exchange. And it probably came through the Harappa Valley civilization, which we don't know how it came. But we probably came through trades in that point. So what Indians were good at was calculation of some of these eclipses, and the calendar was useful. But astronomy, for the most part, was a practical science, because you have to say when you are going to plant your, you need a calendar to see when you do planting. So the Egyptians were pretty good at it. The Indians were also very good at it. The Indian calendar used to be on the lunar system, but with a solar correction. Most other lunar calendars, basically, if you look at Ramzan, it shifts through the various things. The Indian calendar didn't, because they knew it was a solar correction. So there are interesting bits and pieces in there. Most civilizations actually focused on a certain few stars, and that is what they did this. And Mayank Vaya, who was my colleague, his description was, most of them got up, I can see this star, okay, I can do this, now I'm going off to sleep, I'm not going to observe the rest of that. But there are interesting things. For example, very famous in the Bayeux tapestry in the 1066, there's a huge tapestry somewhere in Europe, and in there you have this thing at the back, which is actually the Halley's Comet. So there are things like this various cultures have seen. So there's things written in Indian things, which you can go back and see they probably saw a supernova explosion. The Chinese actually saw the supernova explosion for one of them, which is in the Chinese text. The problem with Indian history is a lot of our traditions are oral. It was not written down. Almost certainly we saw that, so it is not seen. But the lots our mathematical methods were very good. Aryabhatta and all.
Wasn't it? I mean, what she was mostly in celestial mechanics and
It's mostly in celestial mechanics.
and spherical trigonometry.
Yes,
right?
they were excellent mathematicians. So they could calculate various things very, very well. So they were looking at the stars by doing mathematics, not so much just observing. Yeah.
I mean, there is no evidence that during those times the methods such as regression were known. I mean, at least. I mean, nobody has claimed that yet.
Yes.
Arnav, I have a follow-up question.
Sure.
Like for exoplanets with surface and not the gaseous ones, right? So the distinction between the rocky and the gaseous one. So I do see a lot of modeling approaches come out which predict the surface temperature from the equilibrium temperature, right? But the point is, if you do not have surface at all, right? What's the, first of all, why do people do this? And I mean, what's the big picture out of this? I mean, let's assume that you could achieve a pretty good, forecasting, right? But what are you going to do with it? Because you don't have surface and you are predicting surface temperature.
You just hope. It is more that you get data so that when you can find stuff that's Earth-like, you can identify it, right? So you want to fit every one of those. It's not like you will get anything useful. Some of them are molten. They're so close, they can't have an atmosphere. You can work out the density. So you want to work out the range of density. So see, otherwise all our assumption is the density is what we have here. One of the problems, for example, in our solar system, the assumption is at the center of Jupiter, there is basically a terrestrial planet. So some of the density, essentially you have an Earth-like planet, molten thing in the center. There are lots of arguments about what the density is, what the mass is, how large that is. This is in Jupiter itself, the data that you have. So there is some use of when you have this extrasolar planets, because it has surprised us all the way through, is let's see what range of density we have. There's other materials that could have formed terrestrial planets, and how long it lasts if you're really close by. Can you predict how quickly it will melt away, and then how that will show up in the statistics of all the planets you're looking? And your observational statistics will depend on how long some of these survive. So people can do Monte Carlo modeling of all of those. So even though that itself is not useful, it is useful in setting the parameters for everything else. I remember when we got the hot Jupiter, the people in our department were working in, it can't be true, this can't last in the reason, in fact, one of the American people was actually, he was a graduate from our university, he was a University of Maryland graduate. They would be the first people to actually have discovered this hot Jupiter. They didn't think they think it would take at least 10 or 12 years. We are going to wait for the data of 10 or 12 years. The Swiss guys looked at 4 days of data and found it. So this is the same thing in the terrestrial planet also. We should not make the assumption that we know what we have. We should look at all the density distributions, the size distributions, and we might find the net distribution that you get is very different from what we get in the Milky Way. Just because we have got iron and silicon in this, it might not be, because the stars that it's forming from are different. Most likely, those have basically been ejected from planetary systems. If you have a nearby star pass by or far away, gravitationally, you can actually peel them off. They probably did not form free. It's very unlikely that there are processes for them to be free floating, but it is very likely that they will be kicked out, because this is how you get comets, right? So you have this comet cloud, but something else happens, and sometimes a passing star. We get a cloud of comets coming, the passing star kind of changes the gravitational orbits. And if you have large enough planets far enough away, the sun is flying by others, even that little bit of perturbation might be enough for them to lose them into the interstellar space. It is. So you get them with microlensing and all of these. You get them by luck, basically. But then all of this, you can turn around the statistics and say, what does it say? If you are looking at this patch of sky, only see this, you can turn that statistics around and say how many of them are free floating and how many should you have seen. And it's a fairly small fraction. You have to be lucky, and then you have to work statistics out of the lucky stuff. But that's... I mean, look, if you have the first generation of stars, they've got only hydrogen, helium, and lithium. The fact that we have iron and everything else on that means that the sun is the second generation star, which is formed from the supernova remnant of everything else. And the word for that is we are all made of stardust. So everything that we are made of was made in another star before we this. Okay, thank you very much.
Okay, let's